Hello, I'm Nadim Ahmed, one of the authors of the paper that I would like to present today. So this work has been accepted fourth posting in ML workshop co-located with ICML. The title of the paper is Stabilizing the Kuramoto Equation Using Deep Learning with a DeepONet-guided. So the authors are me, Nadim Ahmed, lecturer in Independent University of Bangladesh, and the co-authors are MD Ashraful Babu, Professor Independent University Bangladesh, MD Mortuza Ahmed, Professor American International University Bangladesh, A. Mostafizur Rahman, Professor American International University Bangladesh, and corresponding author Mahmud, Professor King Fahd University of Petroleum and Mineral, Saudi Arabia. So what's the motivation of the current? So the motivation is the controlling chaotic system, such as uh, any fluid flows or flame fronts or any other physical phenomena or engineering application remains core challenge. Especially the Kuramoto-Sivashinsky equation, that means K's equation plays a key role in the chaotic phenomena as it captured spatio-temporal chaos. Yet the conventional methods has some drawback since the model-dependent controllers scale poorly. So our data-driven, adaptive, and model-free strategy is really very essential. So few study exist, either operator learning or RL. So few study exist, but to the best of our knowledge, there is no study which combines the generalization power of operator learning and adaptive power of RL. This is the main motivation. We combine it. So the key contribution of the paper is we present hybrid control combining DeepONet, which is deep operator learning, with model-free RL. So we used hybrid control to stabilize chaotic, and we present two-stage framework. In offline, we use DeepONet to learn generalized control, and in online, we use Deep Deterministic Policy Gradient agent to refine the control learned by the DeepONet. So we got an outstanding performance of our hybrid model. It achieves up to 85% energy reduction, which is outperforming the traditional feedback. So let's dive deeper into the methodology. So here is the case equation. We design f of xt. We control f of xt to find the optimal u, to find the optimal state u. So that the energy is minimized. So here we can see here is the energy equation. So how did we do this? Especially, firstly, we used a spectral method for numerical solution. The case equation has been solved using Fourier spectral methods. Especially, our control signal is injected in a spectral space, and we recovered it using fast Fourier transformation, inverse fast Fourier transformation. So, in the spectral space, Fourier space, here is the equation here is the equation which represents the Ks equation. So the Ks equation becomes this type of equation in Fourier space. So then we use this 2000 noisy trajectory to train our DeepONet. So here from the figure 1, we can see that in the left hand side, uh, here is the DeepONet architecture. So basically, DeepONet has two neural network. One is branch network, or another is trunk network, and combining these, we essentially maps U to F from U to optimal F. So we call it F prior. As DeepONet operator learning maps one function to another function, we maps U to F. So then we use deep deterministic policy gradient, which adds residual action AT to refine the prior DeepONet's control. So especially we combine this to learn the total control CXT. So this was the methodology. So our uh, hybrid methods performs very well, really well. As we can see from the figure 2, the red line represents the energy line of the traditional control, and the blue line represents the energy line for our method. So here is energy is much more lower. So 55% energy drop in the first 0.2 time units, which is 5 times overall reduction. So the training was really good. DeepONet MSC decreases 99.3%, and RL mean reward increases 59.3%. So on the other hand, our RL, our agent maintains U within -8 to 4, which is very good regarding stabilizing the chaotic system versus the classical feedbacks -16 to 12. So the conclusion is DeepONet-guided RL delivers robust and low energy stabilization for case system, which has a very potential uh, for controlling further 3D turbulence or multiphysics, PD, so on and so forth. Thank you.